Welcome to AI Frontiers, where cutting-edge research meets accessible insight. Today we're exploring 5 groundbreaking robotics papers from August 19, 2025, that are reshaping how robots perceive, navigate, and interact with our world. From spatial memory breakthroughs to social intelligence advances, we'll journey through embodied AI innovations that promise to transform silicon minds into capable physical partners. Picture this scenario. A robot stands frozen in a hospital corridor, facing 2 identical-looking doors leading to patient rooms. Traditional visual systems would make an educated guess, potentially sending critical medical supplies to the wrong patient. This represents a fundamental challenge in robotics. When environments contain repetitive visual features, how can machines maintain spatial accuracy? The breakthrough we'll explore today teaches robots to think like detectives, using not just what they see, but how they move to solve these spatial mysteries. This approach combines visual perception with trajectory analysis, creating a more robust understanding of space and location. These research advances represent fundamental paradigm shifts rather than incremental improvements. We're witnessing robots develop human-like visual processing capabilities, athletic-level movement precision, and philosophical reasoning abilities. The integration of these capabilities enables operation in complex, real-world environments where traditional approaches fail. This transformation extends beyond laboratory demonstrations to practical applications in healthcare, manufacturing, and domestic settings. The convergence of perception, cognition, and physical embodiment creates unprecedented opportunities for human-robot collaboration. Computer science robotics operates like a grand symphony orchestra, where multiple disciplines harmonize to create intelligent motion. Computer science provides the algorithmic sheet music, the mathematical frameworks and computational logic that guide decision-making. Mechanical engineering supplies the physical instruments, sensors, actuators, and structural components that enable interaction with the world. Artificial intelligence serves as the conductor, orchestrating these elements into coordinated performance. Unlike traditional orchestras performing in controlled concert halls, robotic systems must execute their symphonies in unpredictable real-world environments, where the stage constantly changes and unexpected obstacles appear. Our first major theme centers on robust perception and memory in challenging environments. The ROVER system, developed by you and colleagues, addresses the notorious loop closure detection problem in robotics. Like skilled navigators who combine visual landmarks with dead reckoning techniques, when navigating through fog, modern robots are learning to integrate visual information with trajectory data. This approach helps robots maintain accurate spatial maps, even in repetitive environments where traditional vision-based methods fail. The breakthrough lies in recognizing that movement patterns provide crucial constraints for verifying spatial relationships, enabling robots to remember familiar locations with unprecedented accuracy. Multi-agent social navigation represents our second critical theme, addressing coordination challenges when multiple robots operate in shared spaces. Imagine a crowded dance floor where couples must coordinate not only with their partners but also avoid collisions with other dancers. This perfectly captures the challenge facing robotic systems in constrained environments. The comprehensive social minigames framework provides the first unified approach to understanding these complex interactions. Research reveals that traditional multi-robot coordination methods, designed for open environments with ample maneuvering space, fail catastrophically in constrained scenarios like hospital corridors, office buildings, and residential spaces, where precise coordination becomes essential. Language grounding and instruction following forms our third theme, tackling the fundamental challenge of bridging human communication with robotic action. The CAST method demonstrates remarkable progress, achieving a 27% improvement in navigation task success rates through counterfactual reasoning. This approach is analogous to teaching someone to dance using only verbal instructions, requiring precise mapping between linguistic concepts and physical actions. CAST generates alternative language action pairs for training, forcing robots to learn more nuanced associations between words and behaviors. This breakthrough suggests that instruction following limitations stem not from architectural constraints, but from training data diversity and quality. 4 breakthrough discoveries emerge from this research, each representing a fundamental shift in robotic capabilities. First, trajectory-aware robot memory solves visual confusion by incorporating movement patterns as verification constraints. Second, social navigation taxonomy reveals common underlying structures across seemingly different coordination problems. Third, counterfactual learning approaches achieve substantial task performance improvements by generating alternative scenarios during training. Fourth, advanced control theory translates into practical improvements for real-world robotic systems, demonstrating that sophisticated mathematical frameworks can enhance operational performance. These discoveries collectively point toward more capable, reliable, and intelligent robotic systems. Today's paper of the day, ROVER, Robust Loop Closure Verification with Trajectory Prior in Repetitive Environments by you and colleagues, exemplifies how elegant theoretical insights solve persistent practical problems. The research addresses a frustration familiar to every robotics researcher: robots navigating through environments with repetitive visual features like identical doorways and similar corridor segments. Traditional visual SLAM systems face nightmare scenarios in these settings, potentially declaring false loop closures based on visual similarity alone. ROVER introduces a revolutionary approach that treats trajectory information as a powerful verification constraint, like a detective who examines not just fingerprints, but also whether the suspect could physically have been present given their known movements. ROVER's revolutionary approach transforms loop closure verification from purely visual recognition to comprehensive motion consistency analysis. When visual systems suggest potential loop closures, ROVER doesn't simply accept or reject based on appearance similarity. Instead, it estimates what the complete robot trajectory would have been if the proposed loop closure is correct, then evaluates this trajectory against known motion capabilities and constraints. The system identifies trajectories requiring impossible robot motions, such as instantaneous teleportation or physically implausible speeds, and rejects these regardless of visual similarity. This mirrors human spatial reasoning, where we naturally consider not just what we see, but whether our current location makes sense given our recent movements. ROVER's impact extends far beyond loop closure verification, introducing the trajectory prior paradigm that could transform robotic perception systems. Experimental validation demonstrates significant precision improvements across challenging indoor and outdoor environments with repetitive structures. The system integrates seamlessly with existing SLAM frameworks without requiring major architectural modifications. Most importantly, ROVER enables human-like spatial understanding by giving robots the equivalent of spatial common sense, the ability to reason about whether their perceived location is consistent with their movement history. This represents a foundation for next-generation robotic perception systems that combine multiple information sources for robust environmental understanding. Looking toward the future, robotics research resembles the early days of the Internet. Tremendous potential is visible, but fundamental protocols and standards for seamless human-society integration are still being developed. Integration of large language models with robotic systems promises robots capable of contextual understanding, meaningful dialogue, and collaborative problem-solving. Multi-robot coordination is evolving from simple swarm behaviors to sophisticated social intelligence, requiring navigation of both physical and social spaces. Standardized benchmarking tools will democratize robotics development, accelerating innovation through better measurement and comparison capabilities. Most significantly, we're moving toward lifelong learning robots that continuously adapt and improve throughout their operational lives, becoming true learning partners rather than static programmed tools. Today's exploration reveals robotics research in the midst of remarkable transformation. ROVER demonstrates that powerful solutions often emerge from cleverly utilizing existing information rather than adding complexity. Social minigames frameworks highlight the importance of systematic thinking about seemingly simple coordination problems. CAST methodology shows how counterfactual reasoning dramatically improves learning efficiency in language grounding tasks. Advanced control theory successfully translates sophisticated mathematical concepts into practical real-world improvements. These advances collectively point toward a future where robots function not merely as tools, but as capable partners in human endeavors, emphasizing collaboration and augmentation over replacement. The synthesis of this research content utilized Claude Sonnet-4-20250514 model for comprehensive analysis and summarization of technical papers. Text-to-speech synthesis was powered by Deepgram technology to ensure natural, clear audio delivery. Image generation leveraged OpenAI systems to create relevant visual content supporting the research themes. Human expert review verified the accuracy and accessibility of synthesized content, though potential oversights may exist in complex technical interpretations. All original research references are provided for verification and deeper exploration of the presented concepts and methodologies. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from archive preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Subscribe to AI Frontiers for cutting-edge research insights and join our growing community of forward-thinking technologists. Share your thoughts on these robotics developments with colleagues and engage in public discourse shaping robotic policy. Your perspective influences tomorrow's intelligent machines, and the robots of the future will be better for having heard your voice in this important conversation.